So NASA just put out another alert about this comet called 3I Atlas. And honestly, at this point, I don't even know what to call this thing anymore. Every single time we think we've got it figured out, every time the data starts making sense and we can finally say, okay, this is what's happening, the next batch of observations comes in and throws everything sideways again. It's like trying to nail down smoke. You think you've got it contained, and then it just drifts somewhere else entirely. If you've been keeping up with this whole saga, you know what I'm talking about. This isn't some normal, predictable comet doing what comets are supposed to do. This thing keeps changing, keeps shifting, keeps rewriting its own story as it moves through our solar system. And what changed today might actually be the strongest indication yet that we're watching something truly unusual unfold in real time. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Let me break down what's actually happening here. Because this latest alert isn't just about some weird brightness fluctuation or a pretty new feature showing up in the images. Those things are interesting, sure, but what we're seeing now goes deeper than that. This time, the shift showed up first in the orbit itself. So here's how this works. Overnight, various tracking stations around the world, fed in a fresh batch of really precise position measurements, same telescopes looking at the same object, using the same data reduction methods they always use. Nothing changed in how we're observing this thing. But when all those new position measurements got plugged into the orbit calculation software, something didn't match up the way it should have. The residuals started acting weird. And if you're not familiar with that term, residuals are basically the tiny differences between where the math says the comet should be and where we actually see it in the sky. In a perfect world with perfect calculations, those residuals would be 0. But we don't live in a perfect world, so there are always small differences. The key thing is, those differences should be random and small. They should scatter around evenly. But that's not what happened. The residuals didn't just get slightly bigger. They lined up in a pattern, all pointing in a new direction. And that's significant because it means something about the comet's motion has fundamentally changed. See, with a normal asteroid or a dead comet nucleus, you can predict the orbit really precisely using just gravity. The sun pulls on it. The planets pull on it a tiny bit. You do the math, and you know exactly where it should be. But 3I Atlas isn't a dead rock. It's an active comet, which means it's constantly venting gas and dust from its surface. And when that material shoots off in one direction, Newton's third law kicks in. For every action, there's an equal and opposite reaction. The comet gets pushed in the opposite direction. We call that a non-gravitational force. It's like a tiny rocket engine that's always firing, nudging the comet off the path that pure gravity would give it. And up until yesterday, we had that non-gravitational push pretty well characterized. We knew which direction it was pointing. We knew roughly how strong it was. The orbit calculations accounted for it, and everything matched up reasonably well. But today, to make the new observations fit, that push has to be tilted in a different direction. The thrust vector from the comet's jets has rotated, not by a huge amount, but enough that the software can't ignore it. The math doesn't work unless we assume something about the comet's activity has changed. Now, that alone would be enough to get people's attention. When a comet suddenly starts pushing itself in a different direction, that's worth noting. But here's where it gets really interesting, because while the orbit team was trying to figure out what was going on with the numbers, the imaging team finished processing a completely separate set of observations. They'd stacked together multiple exposures from different observatories to create really high contrast images of the comet's inner region. And of course, because the universe apparently loves to be consistent, the pictures tell exactly the same story as the orbit calculations. In the previous set of images from last week, the inner coma and the main jet had settled into what looked like a stable pattern. You could look at it and think, okay, this is the current configuration. This is how the comet is venting right now. But today's images show something different. The inner coma, that bright fuzzy region right around the nucleus, is skewed in a slightly different direction than it was before. The brightest part of that glow has moved, and the main jet, the most prominent stream of material coming off the comet, has tilted. It's leaning in a new direction compared to where it was pointing last week. And it's not just the main jet. The secondary features, those smaller streams and fans of material, they've rebalanced too. The whole structure has reorganized itself, even way out in the background. The tail of the comet has picked up this subtle S-curve that wasn't there in earlier images. It's like the whole thing twisted slightly. So now you've got two completely independent lines of evidence pointing to the same conclusion. The orbit calculations say the net force acting on the comet has rotated. The images show that the actual jets and streams of material being thrown off the nucleus have rotated with it. That's not a coincidence. That's not a data processing error. That's real physical change happening on this object in real time. And that's what NASA means when they say 3I Atlas has shifted once more. The comet is actively changing how it's venting, which changes how it's pushing itself, which changes its orbit. All of that is happening right now, while we're watching. So the obvious question becomes, why is this happening? What's going on with this comet that keeps making it change? To understand that, you have to think about what the nucleus of a comet actually is. It's not a solid chunk of rock. It's more like a dirty snowball. Or maybe a better description would be a fragile pile of frozen rubble barely held together by its own weak gravity. The surface is covered with a crust of dark material, organic compounds that have been processed by radiation over millions or billions of years. But underneath that crust, there are pockets and layers of volatile ices, things like water ice, carbon monoxide ice, carbon dioxide ice, all frozen together with dust and rocky grains. When a comet gets close to the sun, that ice starts to heat up. Not evenly, though. The sun only directly heats whatever side is facing it at any given moment, and the crust doesn't conduct heat very well, so the energy takes time to soak down into the deeper layers. As the temperature rises, those volatile ices start to sublimate, turning directly from solid to gas without melting first. The gas builds up pressure underneath the crust until something gives. A crack opens up or a weak spot fails, and suddenly you've got a jet. High-pressure gas and entrained dust blasting out into space at hundreds of meters per second. Now, here's the thing. The surface of 3I Atlas is probably like a patchwork of different features. You've got sealed-up fractures, frozen-over vents from previous activity, pockets of volatile material at different depths, all scattered across the nucleus in no particular pattern. For the last several months, it looks like one particular vent or group of vents has been doing most of the work. One big fracture on the surface has been wide open, venting steadily, producing that dominant jet we've been seeing in the images. And because it's been fairly steady, the non-gravitational push on the comet has been fairly steady too. But the comet has been out here for months now, heating and cooling and stressing as it swings past the sun and back out again. The deep interior is still catching up to all the energy that soaked in when the comet was closest to the sun. Temperature gradients are shifting. Pressure is building in new places. Cracks that were stable might be getting stressed. And at some point, something gives. One possibility is that a new vent just opened up. Maybe there was a pocket of volatile ice buried under a thin layer of crust on a different part of the nucleus. As the heat finally worked its way down to that depth, the ice reached its breaking point. The pressure built up until it burst through the surface, and suddenly you've got a whole new jet firing from a completely different location. If that new jet is strong enough, if it's pumping out enough gas and dust, it could rival or even overpower the original vent. And the moment that happens, the net push on the comet rotates. The thrust vector shifts, the orbit changes, the images show a new configuration. That's one explanation, and it's pretty straightforward. New vent opens, activity pattern changes, everything shifts. But there's another possibility that's maybe even more interesting. It could be that the whole nucleus is changing how it spins. See, when jets fire off a comet, they don't just push it forward or backward or sideways. They also apply torque. Imagine a spinning ice skater. If they extend their arms, they slow down. If they pull their arms in, they speed up. A comet is kind of similar, except instead of arms, it's got jets firing off at weird angles all over its surface. Every time one of those jets fires, it's applying a tiny twisting force to the nucleus. And over thousands and thousands of rotations, those tiny torques add up. We already know from previous observations that 3I Atlas isn't spinning in some simple, stable way. It's not just rotating smoothly around one fixed axis. The rotation is more complex than that, probably tumbling or precessing in some complicated pattern. And if the spin axis is precessing, if it's slowly wobbling like a tilted spinning top, then the orientation of all the vents changes over time. Even if the vents themselves never move and never change their output, the direction they're pointing in space is constantly shifting, because the whole nucleus is slowly wobbling. If that's what's happening, then today's shift in the thrust direction might just be one more step in that slow, ongoing wobble. The comet isn't necessarily opening new vents. It's just that the vents it already has are pointing in a different direction now, because the whole object has tilted slightly. Both of those explanations make sense. Both fit the data, and honestly, it's probably some combination of both. New vents might be opening while the spin state is also evolving. This thing is complicated. But here's where it gets worrying. Every time the thrust direction changes, every time a new jet comes online or the spin axis tilts, you're redistributing the stress inside this object. Think about it. The nucleus is barely holding itself together. It's not solid. It's not strong. It's a loose pile of ice and rock held together by weak cohesion and weak gravity. When a jet starts firing, it's pulling material off the surface in that area, which changes the mass distribution, which changes how the internal forces balance out. Parts of the surface that were in shadow suddenly get blasted by sunlight reflected off other parts of the comet. Cracks that were stable under one stress regime suddenly get tugged in a different direction under the new regime. Cavities inside the nucleus that were nicely balanced might get pulled or compressed in ways they weren't before. In the short term, over days or weeks, that just looks like what we're seeing now. The comet shifted again. The jets realigned. The orbit needed a new solution. It's interesting, it's dynamic, but it's not necessarily dangerous. But over longer timescales, over months, all those repeated changes in stress start to add up. Every shift is another load that this fragile object has to absorb. Every new configuration is another test of whether the nucleus can hold itself together under these conditions. And we've seen this story before with comets from our own solar system. We've watched comets go through exactly this kind of pattern. Subtle changes in non-gravitational forces, evolving jet structures, slowly increasing rotation rates as the jets spin them up, and then, sometimes, without much warning, a sudden breakup. The nucleus just can't absorb any more stress. Something finally gives, and the whole thing comes apart. It might split into a few large pieces, or it might disintegrate into a cloud of fragments and dust. Either way, the comet as a coherent object ceases to exist. Now, I want to be really clear here. Nobody is officially saying that's what's about to happen with 3i Atlas. The language in the alerts and the updates stays very careful. They talk about a new update to the orbital solution, a measurable evolution in the outgassing direction, a shift in the net non-gravitational acceleration. All very technical, very measured, very precise language. But here's the thing. You don't schedule extra telescope time. You don't push observatories to collect denser data more frequently. You don't send out internal alerts to other research groups because you think everything is fine and boring. You do all that because you know something interesting is happening, something that might develop into something significant. You do it because this object is active in a way that matters, in a way that could lead somewhere unexpected. So what's the bottom line here? The bottom line is that 3i Atlas is not just coasting peacefully out of the solar system on some fixed, predictable trajectory. It's not done. It's still burning, still venting, still actively adjusting its own motion layer by layer, vent by vent, rotation by rotation, day by day. Yesterday's shift wasn't the final word. Today it shifted again. And if that pattern continues, if every new orbit solution needs a different thrust direction, if every new set of images shows the jets leaning a little bit further, then what we're watching here is essentially a live experiment. We're seeing in real time how an interstellar comet responds to its one and only close encounter with our sun. This thing came from somewhere else. It formed around a different star, in a different planetary system, maybe billions of years ago. It's been drifting through the cold emptiness of interstellar space for an unimaginably long time. Frozen solid, completely dormant, just slowly tumbling through the dark, and then by chance, its trajectory happened to intersect with our solar system. It fell in toward our sun, heated up for the first time in who knows how long, and started doing what comets do: venting, outgassing, developing jets and a coma and a tail. But it's doing all of this with a structure and composition that evolved under completely different conditions than our own solar system's comets. We don't know how dense it is, how strong it is, how volatile its ices are, how its interior is structured. We're learning all of that by watching it react. And what we're learning is that it's unstable. It's dynamic. It keeps changing. Maybe it stabilizes eventually. Maybe in another few weeks or months, the activity settles down into one final configuration, and the comet just limps away relatively intact, slowly fading as it heads back out into interstellar space. Or maybe it keeps shifting. Maybe the stress keeps building. Maybe one more vent opens, or one more wobble in the spin state redistributes the load just a little bit too much, and something fundamental gives way. We don't know yet. That's what makes this fascinating and frustrating at the same time. This alert today is just another data point in an ongoing story. It's another reminder that we can't just look at 3i Atlas once, write down some numbers, and call it done. Every time we look, something has changed. Every update raises new questions. Will the next alert say that 3i Atlas finally calmed down and stabilized? Or will it say that it shifted again, and this time even more dramatically than before? We won't know until we keep watching, and that's exactly what's happening. Observatories around the world are keeping their eyes on this thing. Every clear night, someone somewhere is collecting more data. The orbit keeps getting refined. The images keep getting sharper. The models keep getting updated. And every few days or weeks, we get another piece of the puzzle. This is what makes observing comets so compelling. They're not static. They're not predictable. They're these fragile, dynamic, evolving objects that constantly surprise us. And when that comet happens to be a visitor from another star system, when it's literally the only sample we have of what comets look like out there in the wider galaxy, every little change becomes incredibly important. So yeah, 3i Atlas shifted again, the jets rotated, the orbit changed, the thrust vector tilted. It's one more step in a process we're still trying to understand,